Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, number of beautiful partitions. So the problem is interesting. If you are a regular viewer of this channel, I am very sure that you should be able to come up with a n square k kind of solution. Okay, if you haven't, I would strongly encourage you to think a bit before moving forward. In this particular video we will be trying to understand if we are able to come up with recursion, how to convert that recursion into top down into bottom up solution. Okay, so in this channel we have solved this kind of problems before, but we haven't really thought about how to take it step by step. So I would try to make you understand that, and this video can be a little long, so bear with me. But as usual, I can ensure that if you watch till the end, you should be able to learn something new, and going forward you should be able to apply, or at least think in that direction of how to convert a top down solution into a bottom up approach. Okay, so with that, let's get started. The problem states that you are given a string s that consists of digits from 1 to 9. Okay, and you are given two other integers k and min length. The problem is you have to partition the string s into k non-intersecting substrings. Okay, remember partition, you can't skip anything. Okay, second, each substring should have length at least min length. Okay, and the third condition is you have to, like, each of the substring that you choose should start with a prime digit and should end with a non-prime digit. What are prime digit? Prime digit are given as 2, 3, 5, and 7. On all other digits between 1 to 9, excluding 2, 3, 5, 7, are non-prime digits. Okay. So if you are able to partition S such that it satisfies all the three conditions, then that particular partition is called a beautiful partition. And the problem is you have to count the number of beautiful partitions. And as usual, since the answer can be large, you have to return it modulo 10 to the power 9 plus 7. Okay, so notice, so there are, let's say this is the example. Let's say this is the string s, k is 3, which means you have to partition it into three substrings. Min length is 2. It denotes that each of those partition can have at least length 2. Okay, or should have at least length 2. Now what they have done, like they have shown three different kind of partitions. So let's talk about this partition first. Here you can see it has length greater than equals to 2, so that's fine. It has exactly three partition, like each of these ha- is less than equals to, each of this is less than equals to 2 of length, and each of these, like there are total three of them. Okay, so these two conditions are satisfied. Now, sorry, these two conditions are satisfied. Now the last condition, each of them should start with a prime and ends with a non-prime. Starts with a prime, ends with a non-prime, starts with a prime and ends with a non-prime. So third condition is also satisfied. So that's where this is a valid partition, and you can see all these three are valid partitions. Okay, so the answer is 3 because you can actually get only these three valid partitions. Other than this, there is no other valid partition. So that's why the answer is 3. So hope the problem statement is clear. Okay, so let's take it step by step. We have to find the number of beautiful partitions, and the condition is each of those partitions should satisfy these three conditions. Like there are total k of them. Each partition should have length of at least min length, right? And each should start with either one of these and ends with one of these, right? Now, uh, again, if you haven't tried the recursive approach yet, I would strongly encourage you to pause and think. Okay, let's start. So you have, think about it. You have these three conditions. Okay, now, uh, what is the first partition that you can choose among these three conditions? You have to satisfy. like this condition is satisfied after every partition is chosen. So let's forget about this for now. These two conditions apply with every partition, that each of them should have at least this length, and each of them should start with one of these and ends with one of these. Okay. So first thing is each of them should start with this. Let's say min length is 2 for now. Now, if min length is 2, what is the first partition? First partition can be this, or can be this, or this, or this, and so on and so forth, right? Now, let's say like this is the valid, or these are the probable candidates for the first partition, but among them, ones that satisfy this as well are the candidates. So let's see, this starts with 2. So the first condition is satisfied. Now it should end with one of these. So now we know that it starts with 2 and it should have a length at least 2. So can this be a valid partition? Answer is no, because end should be one of these. So this is not a valid candidate. Can this be a valid candidate? Again, answer is no, because 5 is not in one of these numbers. Okay. Now this can be valid partition, right? Now if this is a valid partition, what are we left with? We can say that okay, we have taken one partition already. Now tell me how many ways are there to partition this string, the remaining string, into k minus 1 partition. Initially you have to partition it entire string into k partition, but because you have taken out one partition already, you are saying give me the number of ways in which I can partition this remaining string into k minus 1 partitions. This problem is exactly similar to the original problem, where we are saying that give me the number of partitions for this entire for partitioning, give me the number of ways to partition this entire string into k partitions. Now you are saying give me the number of ways to partition this entire string into k minus 1 partition. So exact same problem with reduced constant. So you can see the recursion here, right? So what you will do, you will try, let's say f of I and p, where I is the starting index. So I denotes the starting index after which you are considering the array. So let's say you want to find the number of partitions for this particular substring. I would be this particular index. Okay. So f of I and p is the number of partition that you want. So what you will do, you will try out every possible j dash that can be a valid partition. So you will try every possible j dash and just sum them all up, and that will be your answer, right? Does this make sense? So basically what we are doing is we are finding out first partition, and first partition, for first, like how we are selecting the first partition we are selecting by satisfying these two conditions, that the partition length should be at least this, and the partition should start with one of these and ends with one of these. Okay. So what we have done, we have started with our index I. Let's say this is the I initially. So we started with our index I. We take every partition of length this and greater than this, and see which of them have uh, ending index as one of these, right? So for example, here we see that this starts with 2, but the next one and the length, minimum length required is 2. So this should be the minimum partition. But this doesn't satisfy the second condition. So we go on and we found that this partition satisfies this condition. So this is our first J dash, right? This is our first J dash. Now second, like what we will do, we'll just find out what is the number of, sorry, this is our first J dash. This one is the first J dash, because this the partition ends here. So this is the number of, this is the remaining string, and you want to partition this remaining string into k minus 1 partition or p minus 1 partitions, right? So hope you get the intuition. So what would be the recursion look like? The recursion would look like some this. So if index is n, it means you are at the end of the string, you have exhausted the entire string. If this is the case, then string is empty, right? So empty string can be partitioned into zero partition, right? So that's why we are checking if partition is zero, then return one, otherwise return zero, right? If partition is zero, it means that you are at the like you are somewhere before the end, right? Let's say you are here, and you are saying that for the remaining string, find me the number of ways to partition it into zero partition. So that is not possible, right? You have to partition it at least one partition. So that's why we return zero. Second, what we checked, like initially each partition should start with a prime, right? A prime digit. So what we are checking is if the current starting index is a prime or not. If it is not prime, we return zero, because we know that this cannot be the start of a valid partition. Okay. Now we know that this is the valid start. So this condition, this particular condition is satisfied. Okay. Now what we want is we want to iterate over every partition, every valid partition. So what, like we will just iterate over the ending index of this particular partition. This starts with this particular index, it should end somewhere. So that somewhere should have length of at least min length. So that's why we're starting with this particular index. And what we are checking if this particular index is prime or not. If it is prime, we will continue, because what we want is the ending index should be non-prime. So if it is prime, we continue. Otherwise, if it is non-prime, then we found a valid partition. So this, let's say this is the example. We found a valid partition. So now if we found a valid partition, we can just divide the problem into a smaller problem, wherein we are saying for the remaining string, find me the number of ways to partition it into one less partition. Okay. So we will do this for every valid end index and sum them up, and that will be your answer. Okay. So hope this entire solution makes sense. Now what will be the time complexity? Remember that you can do memoization. So each of these state you will be calculating only once, right? So how many different indexes you can have? N, right? How many different partitions you can have? K. So total number of unique index comma partition would be n into k, right? So there are total these many number of states. Now for each of these states, what you're doing, you are doing some order one operation, that is fine, and then you have a for loop which runs over the leftover string. So in worst case, this can go up to order n. So for each of these state, you are performing order n kind of operation. So in total, your complexity is order n square k. Okay. Now this will not pass because the value of n and k both is 1000. So this would surely not pass. So what now we have to do? So we come up with recursion, we memoized it. After memoization as well, we saw that the solution is n square k. So then the first thing that you should think of, which of these can you remove? Can you remove n or k? You can't, right? Because that is your state. So you can't remove this. You have to remove this n somehow, right? So how would you remove this n? In this particular case, you have to iterate over, like you have to iterate over each of the valid end index, right? And in worst case, this end index can be order n. Okay. So you can't actually avoid this n with this current approach. That is clear. Now there are two choices. Either you come up with some mathematical formula and prove that this result, like the sum of this result or this entire for loop for every partition, will not go above some x. So that would be like you are doing some some mathematics and finding out that okay, worst case analysis of this would not be order n square k, but rather be order nk plus something. Okay. So that is a different path that you can take from here. But other thing that you can try is you can see this state. What is this? End plus 1 and partition minus 1. So partition minus 1 is common, right? Partition minus 1 is common across all such f that you are calling, right? And whenever this is the case, like partition, something is common across all your cases, then you can actually think of a bottom up approach, wherein you will say that, okay, I will come from bottom and then do some kind of pre-computation so that this entire sum is something that I can find in order one. Okay, so that is the second path that you can take. Okay, so first mathematics that you can try. In this particular video, we will figure out the second path and why we have taken second path. The reason we have taken the second path is because we saw that one of the parameters in this particular recursion is common across all such indexes which we are iterating over. So if because this parameter is common, we can or we may be able to apply some kind of pre-computation while doing bottom-up approach. Okay, so now if you are new, like bottom-up approach is like here we have what we have done is top-down approach. Basically, we have said that each of these value we don't know about any of these value. We will calculate these values as and when required. Okay, so when you are calling this particular index, you can't be you can't be assured that any of these, like you can't be assured about any of the indexes which is greater than this or smaller than this. They may or may not be calculated because in top down we only calculate the ones which we are required and we calculate it on demand basis. Okay, so moving forward, so let's just demystify what we have just discussed. So we have to simplify the problem, like if I assume that you don't know bottom up at all, so that's why we am simplifying the problem. If you know bottom up, I would encourage you to skip some part of the video. That should be fine. So for now, let's just simplify the problem. Let's assume that min length was not there. So in a sense, we are saying that this condition is not there and length is always 2. Like minimum length is always 2. That's what our assumption is for now. We will relax this a little, but for simplicity, we have assumed this. And because we have assumed this, we this min length we have removed from here. Okay, because we already assumed that min length is not there. Okay, now you have to remove this particular loop, right? And we saw that this partition minus 1 is common across all the indexes which we want. So what you can do in bottom up, you will always, because you want to find out something on partition minus 1 over the next set of indexes, right? So that's where you will start with the last index, because what you want, like let's say you are at index I. So what you want is something in this particular area, right? Like this, let's say this is the end index. So you want something in this particular area. And because you want something in this particular area, you have to calculate this area first. That's where we are starting from the last index. Now, we will calculate the exact same thing. What is the thing? The thing is given index comma partition, tell me if I will start with this particular index, how many ways are there to partition it into this number of partitions? Okay, so currently this is the last index. Now, if you remember, we have said that minimum length is 2. So you can't actually take or make one partition with only one length. So let's just move forward. Okay, now for this, what is the, like you can form one partition, but what is the condition for making one partition? The condition for making one partition is this particular index or the current partition should start with a prime and should end with a non-prime, right? Now, it's like here it starts with a prime, so that is fine. And we are calculating this particular value, which is 1, or what we are saying is only one partition. Like tell me number of ways in which I can form one partition. So number of ways in which you can do one partition will be this index is start this is a valid partition, right? You can have, or you can have a valid partition that is starting from here. So you will start from here, and your ending index your ending index would be one of the indexes afterwards, right? So in this particular case, this is a valid ending index, so you will have one way. Okay. Similarly, if you think about this particular index, right? So you have to form one partition starting at this particular index, right? So this partition, is this a valid starting index? Answer is no. So because this is not a valid starting index, you can't form a partition starting from here, right? Now, coming at this, is this a valid starting index? Answer is yes. So what is, you have to form one partition only. So because you have to form one partition only, you will look at the last index. Last index is also one, okay? And because last index is also one, you can simply say one partition is possible, right? Similarly, let's say you have to form two partition. So you will start with this particular index, and you will iterate over next index. So you will say that, okay, this is a valid ending partition. Now, because this is a valid ending partition, how many ways are there in which I can form one partition from the remaining string? Like this is the remaining string, right? How many ways are there in which I can form one partition? And what is the value? Value is one. So number of ways in which you can form two partition is one, starting from here. Okay, why one? Again, you started with this partition, and you iterated over all next partition, or the starting index of the next partition. So starting index of next partition would be here, like this is one possible index, right? And because this is a valid ending index for the first partition, you say that, okay, I will take this first partition. Now tell me number of ways in which I can partition the remaining string into one partition, because one partition you have already tried, and you have to make two partitions because this value is one. Like number of ways in which you can partition this index, this remaining string into one partition is one. So that's where you copied this over here. Okay. Uh, Now you will try in this particular index, like this is this particular string, or this particular first partition. This is not a valid partition, right? So because this is not a valid partition, you you will move forward. You will try this particular partition. This is a valid partition because this inset this inset non-prime, but there is no string afterwards, right? So you can't form second partition. So you will only get one partition. You will only get one way to partition this entire string 5131 into two partitions. Okay. Now this will be zero. Why zero? Because you will see you are you will okay, this is one valid partition, right? Now this partition you will you will take, and you will say, okay, what is the number of ways in which I can partition the remaining string 31 into two partition, and that value is zero, right? So you will just copy it over here, and you will try other combination, and there is no other combination left. So this is the zero, this is the value. So hope you get the intuition. Now what exactly we are doing here? So let's just okay, so let's move this around. So we are doing this thing here. So instead of top down, now we have converted this easily into bottom up. And what we have done, we have just said that, okay, this index, we will start from the last index and go up to the first index. Partition, we will start from the first and go up to like a, and we will check whether it is a valid starting index. If it is not a valid starting index, everything is zero. So we have already initialized as zero, so that is the value. If it is a valid starting index or it is a prime, then you will try to find out every next partition. And for every next partition, if that next index is not prime, it means you found a valid ending index. And because you found a valid ending index, you can just add the number of ways in which you can partition the remaining string. So this should be next plus one. Okay, so you can partition the remaining string starting from next plus one into p minus one partition. Okay, so this is exactly same as this. Only thing is we are now sure that if we are at particular index I, everything after I is calculated. We are sure about this, right? Now complexity is still order n square k, but there is an interesting thing here. If you think about this, you are taking for every next index, for every next index which is not prime, you are summing everything of p minus 1, right? Again, for every next index which is not prime, you are summing everything or every such index, the p minus 1 partition of every such index. Okay, in a way, what you are doing is you are summing this entire row up, but only for the ones which is a valid ending index. Okay, so hope this makes sense. Now because we are doing this, we can optimize it much better. So let's think about this. Let's just remove some of these here. Okay, so mm, sorry, so let's continue. Okay, so you are starting from this particular index, right? So for every next, like, you have to sum this entire row. Like for the, let's say you want to find out this particular answer, that I want to find the number of ways to partition this entire string into two partition. So you want this particular value. Now for this particular value, you saw that you have to sum values from here, right? You have to sum values from here. Now you can't sum everything from here. If you are able, if this condition, if condition is not there, what you can simply do, you can just simply maintain a suffix sum, and that should be fine. But you can't do that. The reason being, you have to selectively choose something, and this something would be true for every value of this, or every such index that want to be partitioned into two partitions. So for each cell of this particular row, right, whatever you will take for this row will be valid for each of these, right? So you can still maintain suffix sum. You can still maintain suffix sum, but you will only consider those which are not prime. Okay, hope this makes sense. So this would be next plus one, right? So okay, let's do this right away. Now you will consider only those which is not prime, or basically you will consider only those for which the previous value is not prime, right? So you are adding next plus 1 p minus 1 if next is not prime, right? So you will consider, while calculating suffix sum, you will consider only those which are not prime. Okay, so hope this makes sense. Now let's calculate this again. uh, this 100 is fine, that is okay. Now you maintain a suffix array as well, or suffix sum array as well. So this is your suffix sum array. Now what exactly is the is the value here? So you will consider, you get up till this everything is zero, so you don't need to worry about it. Now here you get first one. Okay, now will you, before calculating anything for this particular column, you will first uh, calculate what is the suffix sum, or basically this particular array. Now what exactly you want at this array? You want the indexes for which the previous one is not prime. So you got a 1 here. So will this one be added in the first suffix sum? Answer is yes, because the previous value is not prime. The current is 3, but previous is not prime. So that's where you will just add this 1 to your suffix sum. So your suffix sum, new suffix sum would become 100. Now let's talk about this. You are at 1, so 1, everything is 0. So because everything is 0, why everything is 0 at 1? Because 1 itself is not prime. So this condition would be satisfied. Okay. So now you got 1. Now let's talk about 5. What is the value here? Value here would be 1, because uh, this, like for the first uh, column or the first row can be populated by just looking at the first and the last index, right? So that's where we put it 1 here. Now what is the value here? Value here would be the suffix sum of this particular row, right? Suffix sum of this particular row. That's it. So what is the suffix sum of this particular row? 1. So value here would be 1. That's it. You don't need to iterate over every indexes now. Now what is the value here? Value here would be suffix sum of this particular row. And what is the suffix sum of this particular row? 0. So value here would be 0. Okay. Now before moving to 8, you will add this to your suffix sum. And the condition for adding is if the previous index is not prime. So what is the previous index? 8. It is not prime, right? So this one you will add here. So this one with, so let's remove this one at all. Now, so this one would become 2. This 0 would become 1, and this 0 would become would remain 0, right? So we add this one to here, this one to here, and this 0 to here, right? Now what is the value here? This would be 0, because again 8 is not prime, so it can't be a valid starting index. This is again 0, 1 is not prime, right? Now what is the value here? This would be 1, because we calculated this by looking at the first and the last index. Now what is the value here? The suffix sum of this particular row. And what is suffix sum? Suffix sum is 2, so value here would be 2. And what is the value here? Value here would be suffix sum of for this particular row, which is 1. So value here would be 1. Now let's just think about it. What does 2 mean here? 2 mean here is, if you start with here, you will be able to, there are two ways to partition this particular string into two partition. And what are those two ways? Those two ways are, first way is this, right? And second way is this. Okay, so that's where, that's how you will partition this into two number of partition. Now again, before moving forward, what you will do, you will just find out what is the value before this, which is 4. So this can be added. So you will add this, you will make this 3, you will make this 3, and this would become 1. Okay, now let's move forward. For 4, this would be 0, because 4 is not a valid starting index. For 5, this would be 1. First value will be 1, second value would be the sum of this, so this would be 3, right? And the value here would be 3 again, because this would be the sum of this, which is this particular value. Okay, now will you add this here? Now the answer is no, because the previous index is prime, and for adding it, every index, the previous index should be non-prime. You will not add this here, so this will remain as is, and you will calculate this. So this will again become 133, and again this will not be added here, because of the same reason, the previous value is not prime. Sorry, previous value is prime, so this will again become 133, and this is your final answer. Okay, so hope you got the solution. Now this is what is the complexity of this? Complexity of this is, after calculating the value of every row or every column, before proceeding into second column or previous column, you are iterating over each of this column again to sum the to sum something up, right? So basically, each column you are iterating over twice. So you are iterating over each column twice, and there are n such column. So complexity is order nk, which will pass. Okay. Now think about it. Uh, we have actually simplified the problem by saying that min length is not there, but there is min length. So let's just finally relax that condition. Again, moving forward, before moving forward, I would encourage you to uh, completely understand what we have discussed before, because that's the crux. This is just a small extension to the previous solution that we just discussed. Okay. Now min length is 3. What does this mean? This means that, okay, let's go over here again. So let's say min length is 3. So if min length is 3, this only affect after what index you will be adding. Okay, so currently we are considering everything just after this index, right? So that's where suffix sum is helpful. But now you have to consider, like, it may happen that for this particular index you have to consider everything starting here, right? So basically you have to maintain suffix sum for every indexes. So you will maintain suffix sum of this particular piece, you will maintain suffix sum for this particular piece, you will maintain suffix sum for this particular piece, and so on and so forth. So basically the only thing that you are modifying now is, instead of maintaining one suffix sum array, you are maintaining suffix sum array at each of those indexes, right? So previously, if the value is 331, it means, let's say at this particular index, it means everything summed up till here is 331. But when min length is something, let's say min length is 3, so you can't have two length array, you have to have three length array at least, right? So that's where you will start summing up everything from here, right? So you want this, you want the value, or you want the suffix array at this particular index, which is something you can store. That's the only difference. So let's just look at it. uh, let's say min length is 3. Okay, so because min length is 3, you can't actually make anything with okay, or maybe let's just simplify this a bit. Okay, so let's say this crosses are not there. So I put this crosses for a reason, like maybe you can skip that reason as well. So um, let's say this is there is one more column here. Okay, and which will denote the suffix sum up till here. So suffix sum up till here would be 000. This one would be 1, right? Why? Because the previous index is a not prime number. Okay, so this is 1. So just forget about, if you are okay, let's just leave this also. Okay, so what is the value here? Value here would be 0. Previously the value here was 1, but now the value here is 0. Why? Because min length is 3. So min length is 3, so you can't actually form anything with two length string. So now what is the value here? Value here will again be 0, because this is not a valid starting index. Now what is the value here? Value here would be 1. And what, why you are getting 1? Because you want this particular okay. So before, like, again with the previous thing, before moving forward, you have to actually sum this entire thing up, right? But because everything is 0, I am not summing this up. So this, let's say this is another array which everything is 0 for now. Okay, so now think about it. This is 1. This one we get by just looking at the first and the last index. Now what is the value here? Value here would be the sum of everything which starts at here, right? So you want, what does this particular cell means? This means that give me the number of ways in which I can divide this particular string into two partitions. So what you will say, okay, uh, in this suffix array, I will only consider this particular piece. Okay, so what is this particular, like, how you will get this particular piece? Let's say this is 0. So you will get this, you know that everything is 0 here, so this will be 0 for now. Okay, now let's talk about this. So for suffix array, this is your suffix array. So what exactly will change in suffix array? Because it is 1 and previous index is not prime, so you will add 1 here, right? So this will be your new suffix array, right? So instead of modifying it, or you will just store it in your second array. So this is your suffix array. Now let's move forward one step. So this will be 0, because this is not a valid starting index. Similarly, this will be 0, not a valid starting index. Now because these are zeros, this will still be 100, right? Because you haven't modified suffix array at all. Now this is 2. This is the valid starting index, so this would be 1. Okay. Now what will the value of this? Value of this would be simply 2 plus like mean length is 3. So value of this would be suffix sum of this particular thing. And what is the suffix sum of this particular thing? This is the suffix sum, right? Because sorry, min length is 3, so the value would be suffix sum of this particular piece, right? Suffix sum of this particular piece. And what is the suffix sum of this particular piece? Suffix sum of this particular piece is 1, right? So because suffix sum is 1, this value would be 1, right? So hope you got what we are doing. Previously we have only one suffix sum array, now we have n number of suffix sum array, and we just like for finding a particular value we are looking at just the next index. But now because min length is 3, we will look at the index after 3 indexes. Okay, that's the only difference. So hope you got the solution. Just to reiterate, we started with a recursive solution. We figured out we are able to get order n square k solution which will not pass the complexity. We had two choices there: first to come up with some mathematical approach to solve the problem, or second is to, because there is one thing or one index which is common across all the next set of indexes which we are iterating over, we can actually try to optimize it using bottom up. That's where we first converted this entire solution into a bottom up solution with the same approach and exact same complexity. Now once we have converted that, we figured out that okay, this is nothing but suffix sum, but suffix sum is calculated in some weird, like in some different fashion, wherein is prime, we are looking at whether or we are considering a particular value only if the previous indexes is not prime. Okay, and based on that we calculate the suffix sum, and finally instead of iterating over every possible index, we just looked at the suffix sum and just put that particular value there. Okay, so hope this entire solution makes sense. If you have any doubts, I would strongly encourage you to rewind the video and watch the video again. uh, I am going to present the final code, but I would again encourage you to try it coding yourself, because the coding part is very easy. This all things are just for you to understand how to convert a recursive solution into a bottom up approach, and how to think about optimizations. Okay, so let's look at the code. The code is simple. So basically you can ignore this. This is the recursive approach that I have coded. You can watch it later. uh, what we have done, we have initialized our dp array with 0. Okay, and this dp array is nothing but the suffix sum array, or in our solution this is the second array that, sorry, this is this particular array. Okay, now for each of these, we, like, this is just an implementation detail, you can think about it like this. We are instead of this you can simply look at the first and the last index as well. But in the, what I did, I just took this particular approach for simplifying the solution. So you can forget about this as well. So now if it is prime, if it is prime and next, and the starting index, what is the starting index? Starting index would be j plus min length. So if starting index is valid, then you will move forward. Like you will start, if a starting index is valid, then you will consider that particular value. So basically dp of j and p would simply become dp of start index at p minus 1. Okay, now this dp of j at p currently denotes this value. Okay, but you want suffix sum, and this value would be added to the suffix sum only if the previous index is not prime. So that's what we are checking. We are checking, like, first this is a suffix sum. Okay, now the current value, which is dp of j at p, will be added only if current index is prime. Okay, and previous index is not prime. If both of these conditions satisfied, then we will just add the value to the suffix sum and just make dp of j at p a suffix. So this would be either dp of j plus 1p, or this would be dp of j plus 1p plus current value based on what is the previous index. And once we have calculated this dp, like this dp now contain this dp is now converted into uh, this particular structure. And for every next index we can just look at again this particular structure at the given index which we want. Okay, and finally dp of 0 at k would contain the answer that you want. Okay, and remember I haven't I put this j equals to j not equal to 0 condition intentionally, so that I don't need to maintain these two arrays separately. I can just do everything in single array. So that's where I for the last index I am not modifying this array, and this array whatever the value here would be our answer. Okay, so hope the solution is clear. If you have any doubts, please post them in the comment section below. I would be happy to answer. uh, and I hope you learned something new. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already, and I will see you in the next one. Thank you.